Okay, can everyone hear me fine? Everyone in the back? Cool, awesome. So I really want to talk today about three interesting pieces of physics, and thank you for everyone who showed up all the way to the last section. My name's Ben Keller. I'm a Humboldt fellow at the University of Heidelberg, and I have a bit of a confession to make. Really, my title should be this, but that's weird and ugly. So really what I'm talking about today is L-star galaxies, how they work, how they change, how they form over time. And continuing in the theme, I'd like to do this because they're cool, they're neat. They're right at the peak of the galaxy stellar mass to halo mass relation. They're the most efficient star formers in the universe, and we happen to live in one of these objects. So I'm investigating these, among other tools, with the MUGS-2 simulations. This is a suite of 18 L-star galaxies spanning a range of masses with a variety of merger histories and spin parameters, and with a resolution comparable to the Romulus simulations that have been discussed already. So, of course, we have to see our pretty pictures. And the first thing we wanted to do when studying these simulations was to take a look at the effects of feedback models. We've heard a lot about feedback models over the course of this week, and we really wanted to go back and test how changes that were made since the original MUGS run about 10 years ago in terms of both the feedback physics as well as additional code changes that have improved the accuracy of our hydrodynamics actually change how a galaxy forms. So we took the same initial conditions and simulated it 4 times, once without feedback, once with an older cooling shutoff-based feedback, and twice using a new superbubble-based model. Once with the standard fiducial 10 to the 51 ergs per supernova, and once with twice this energy, to kind of mimic the boosted feedback that you see in things like Eris-2K and the additional forms of feedback that some groups are now using. Now, the superbubble feedback model is a really simple idea. It comes down to the fact that massive stars often form in clusters, which means that their feedback energy and their feedback bubbles overlap one another. So you can treat this thing as a luminosity-driven wind. This luminosity-driven wind generates a hot, diffuse bubble that's surrounded by a cold, swept-up, shocked ISM shell. This bubble is actually evaporating and mixing with this shell as well through this process of thermal conduction that we can model in our code as a subgrid model. And the important thing about this conduction is it's a very strongly self-regulating process. The evaporation rate goes as the temperature to the 5/2 power, which means if the bubble gets too hot, it evaporates quickly, pushing it back to equilibrium. And if it gets too cool, that heating will push it back to equilibrium. So what we found, as we were hoping to see, was that with the addition of this extra bit of physics, not extra energy, but extra physics, we find that the stellar mass to halo mass of this L-star galaxy is well regulated over the entire lifetime of the universe. Compare that to the same energy deposited in this earlier cooling shutoff model, and you end up massively overproducing stars early and having a redshift 0 stellar mass that's about 3 times higher than it should be. Importantly as well, the rotation curve of this galaxy goes from being sharply peaked with a peak circular velocity of about 300 kilometers per second to becoming flat, indicating a bulge to total ratio much closer to that of the real Milky Way. And the reason for this comes down to the way this new feedback model actually drives outflows from this galaxy. If you look at high redshift, you can see that the superbubble model is driving mass loadings of about 10 out of our galaxy. So for every solar mass of stars formed, 10 solar masses are ejected from the ISM. This is important for regulating star formation because you're staving off the fuel that the star formation needs to form more stars, and also importantly, you're removing the bulge-forming gas that accretes at high redshift. You can see that preferentially this superbubble feedback removes low angular momentum gas that would be forming a massive bulge, but by shutting its outflows down at high redshift, or at low redshift, when the more disk-forming high angular momentum gas is accreted, you manage to preserve that thin disk. So it's really essential not just to drive mass-loaded outflows, but to drive them only at high redshift. So we want to then move on to use this full sample to look at the population of L stars and really examine this question of, can supernova set this relation? Because there's this standard picture that below L star, the thing that sets your stellar mass is regulation by stellar processes, and above this L star, regulation by AGN kick in. So by looking at a set of simulations at this L star run only using supernova feedback, we can see if this picture actually works. And so the answer to, can supernova do it all, is of course no. As soon as you reach a halo mass of about 10 to the 12 solar masses, you begin massively overproducing stars 2 to 3 times more than you should be based on abundance matched and weak lensing observations. And for every single one of these galaxies that you overproduce stars, you do that in the bulge, giving you peak circular velocities, in some cases as high as 700 kilometers per second. And the reason for this comes down to a universal scaling between the mass loading of your winds and the mass of your disk or your halo. As soon as you reach a certain characteristic mass, the critical mass of these outflows, your mass loading begins to fall precipitously. And because of that, you end up having more material retained by the galaxy, and that retained material can form stars like gangbusters. This is really interesting because this characteristic mass is also around where simulations and observations suggest strong AGN must kick in. So this is really good evidence for this standard picture of how the stellar mass to halo mass relation is actually set up. But this doesn't tell us why this universal scaling exists and why this critical mass exists at this particular scale. So to understand that, we really have to ask ourselves, how does gas actually move through the CGM? When an outflow is driven out of the ISM of a galaxy, what does it do? Does it mix? Does it flow ballistically? Or does something else kick in? So we really have to think about all of the physics that goes into a cloud of gas moving through the ISM. We have energy and momentum being injected as it leaves. We have gravity and accretion shocks potentially heating it up. We also have hydrodynamic drag removing its momentum, radiative cooling removing its energy. But really all of this can be summed up as a combination of buoyancy and drag. So by treating this as a hydrodynamical object rather than a ballistic particle, this hot fluid, we can actually understand how it's moving. And so buoyancy really comes down to entropy. You can think of the Clausius formal entropy as a function of this term here, K, which comes down to just your temperature and your density. And whether or not a piece of fluid is buoyantly stable, whether it's going to sit where it already is, or unstable, it's going to lift up or fall down, depends on this Schwarzschild criterion, the direction of your entropy gradient. If the entropy gradient points away from the center of the potential well, you're convectively stable. If it points the other direction, you're convectively unstable. And you will oscillate in stable environments about this Brunt-Väisälä frequency. And when we look at particles in our CGM, we see that they're nicely split. The average velocity as a function of the local entropy gradient gives you exactly what you would expect if buoyancy is what's determining flows through the CGM. As soon as your entropy gradient becomes positive and you're positively buoyant, you move upwards. As soon as it becomes negatively buoyant, you move downwards. And we can actually see this if we look at individual particles shown here in gray as well as the colored lines with streaks as a function of their entropy and their radial position, normalized to the virial radius and the virial entropy here. So what you see is particles cool down, join the ISM, are heated by feedback, and then move up buoyantly until they cool and fall back down, continuing this cycle. And importantly, this cycle takes place on a long enough time period that gas that's ejected from the ISM can stay out of the ISM for long enough to actually regulate star formation. The equation of motion that ultimately governs the flow of a buoyant parcel of fluid is quite simple. You can derive it from Euler's momentum equation, and it really just comes down to the buoyancy, or the entropy of the fluid, compared to the entropy of the CGM, a gravity term, and drag. And when you evolve this, you can actually calculate what the superbubble entropy should be at the time of breakout using some simple equations from Weaver 77, and you get a breakout entropy and a halo entropy. And this breakout entropy depends very weakly on the conditions in the ISM, which means it's mostly being set here, this behavior, by the halo entropy. And so you can integrate these equations of motion over time for 3 different masses of stellar cluster, and you'll see once we reach a halo mass of about 10 to the 12 solar masses and push beyond that, even the most massive star clusters that are forming today can no longer actually push outflows beyond their Vireo radius. And as we get up to a few by 10 to the 12 solar masses, you find you're ending up only oscillating just a little bit above the disk, where the density of the CGM is going to be high and where your cooling times are going to be short. This is qualitatively different than the way ballistic outflows go. If you take the same amount of energy, put it in the same amount of mass, and shoot it up ballistically so that it's not slowly accelerated through the CGM via entropy, it'll actually reaccrete in less than 100 megayears for a 2 by 10 to the 12 solar mass halo. The same thing will take over a gigayear to reaccrete. So this is really a very different mechanism for driving outflows. And when we trace the particles in our simulations, we see that it does exactly this. The higher the entropy gradient, the longer the recycling time. So I'd like to change gears now and talk about the last part of my ABCs, chaos. So there's this idea of reproducibility crises in various fields. And when we talk about reproducibility for things like the Agora simulation, we talk about our codes. Are we doing our hydro, our gravity, our subgrid physics doing the same thing? What we don't really talk about is the fact that we're simulating chaotic systems, in-body systems, and we're simulating systems where the initial conditions can have small perturbations in them, going from one simulation code to a next. On top of that, there's a couple of numerical reasons why small perturbations can be introduced over time. And we know from other fields that, in fact, for example, our solar system is chaotic. This classic paper from Laskar and Gatineau that they published in 2009 in Nature, but don't hold that against them, showed that for perturbations of less than a millimeter, certain conditions can cause Mercury to have a collision between Mercury, Mars, Venus with the Earth. So if that doesn't keep you up at night, I don't know what will. We know that in protoplanetary disks, chaotic motion is important. The same initial conditions can produce very different solar systems based on floating point round-off changes alone. And we now know as well that galaxies are chaotic systems. So the difference in stellar mass between 2 identical runs with identical codes, identical initial conditions, identical subgrid physics can produce variations of 10 to 20%. This can be even seen when just looking at a column density map. These are identical initial conditions simulated with identical codes. And timing variations in the mergers of these cosmological galaxies have been seeded by small floating point round-off differences that have been pumped up to macroscopic scales. It's even more intense if you look at the metallicity maps. Luckily for us, we are dealing with systems that are somewhat self-regulated. On the one hand, we have mass conservation, which means the in-body chaos can't push you beyond forming as much baryons as you have into stars. And on the other hand, we also have self-regulation by feedback. But in cases where self-regulation is broken, like strong, intense, violent mergers that drive starbursts, you can end up having identical results that have, or identical initial conditions simulated with identical codes that have variations in the stellar mass by a factor of 2. We can estimate as well how intense this effect is by looking at temporal versus numerical stochasticity. So here are the differences between 2 pairs of runs for 4 different feedback models. And here's the step-to-step variation in just one of these runs. So if you're dealing with studying quantities that vary on short time scales, you really need to be aware of this when making comparisons between different simulations with different feedback physics different subgrid physics, etc. So really, what we should be thinking about is not simulating a point in configuration space through some model to a point elsewhere in that configuration space, and looking at the differences in these points as the way of understanding the differences between these models. What we're doing is we're taking a point from an uncertain cloud of initial conditions, mapping it to a single point in an uncertain cloud of final conditions, and what we really need to understand is the shape of these volumes in order to distinguish the effects of two different physical models. So I'm all out of time now. I'll leave you with my three big conclusions. One, high mass loadings at high redshift are essential to forming L-star galaxies. Two, that entropy is a way of driving these winds much more effectively than simply launching them out ballistically. And three, that galaxies are chaotic systems, and small but noticeable changes can be introduced just by tiny perturbations in either the initial conditions or the numerical algorithms we use. Thank you for sticking through that.
Thank you, Ben. Questions?
Hi, Ben. Great talk.
Thank you.
So at high redshift, we don't expect a hydrostatic halo, and the whole concept of buoyancy depends on pressure equilibrium between the bubble and the hydrostatic halo.
Yes, so this is one of the things that this model doesn't work for is both this kind of very chaotic environment and also for very small dwarfs. So for example, I don't think that this model could be used to explain M82 because its halo or its virial temperature is too low for it to have a stable halo. But we do see in the simulations that while there is a lot of like mergers, cold flows going on, all of that is still embedded in volume filling hot phase. And if the outflows are traveling through the sort of path of least resistance through this hot phase, they can still be accelerated outwards.
You know that Reinhard, you were there when Reinhard Genzel showed his new observations of outflows at high redshift, and he found the mass loading factor is low, but even without that, the velocities are too low for escape.
Yep.
So that would mean you cannot really get rid of your gas at high redshift if these observations are correct. And AGN doesn't do much. You first have to bring the gas into the very center to blow it out. This is inefficient. You can't, through an AGN, blow out a large fraction of the gas that you have in a disk, simply because you first have to funnel it into the very center, which is hard.
So two things with that. The phase of the gas that Reinhardt was probing was 300 H per cc. That's very dense and trained material. We have very poor constraints on how that tells you about the hot material that's outflowing. The second thing is that I didn't show it, but if you look at the velocities of this parcel of gas integrated through this equation of motion, they're never even half the escape velocity. But because they're not being launched ballistically and then accelerated downward, but instead accelerated the whole way through, they don't leave, but they stay in the CGM for a significant fraction of a Hubble time. And if they're in the CGM, they're probably not forming stars.
Yeah, so what are the implications of your entropy-driven winds in terms of the distribution of metals out in the CGM? Do you expect similar distributions of, the profiles of our old friends, oxygen-6, carbon-4, for example?
Yeah, so that's, I haven't done that in detail yet, but it's promising. It looks like this is an easy way of giving you the kind of flat distributions that we see from stuff like cause halos. Yes, yes. I'm going to have a lot more simulations and a lot more theory results very soon. Yeah. Cool.
All right, let's thank Ben once more. Now we have Elad Applebaum, who